somewhat acquainted with some of the weirdness of probability, let's use those probabilities and run some tests. Let's go. We are going to talk about comparing some categorical variables. Thus far, we've been using a lot of quantitative stuff. We're going to talk about some chi-square tests, independence and goodness of fit. We're going to look at contingency tables again. Then we're going to focus for this lesson on the chi-square test of independence, and then I'll show you some chi-square tests of independence in R. Chi-squared! Not chi. Chi. So think back to a few lessons ago. I know it's still in there. It's still in there. What kind of things do we compare when we do an independent samples t-test, and what kind of variables do we need for such a test? We've been mostly dealing with a lot of quantitative variables, but what do we do if we want to compare two categorical variables, like does being male versus female affect which gym you go to, like Gregory versus the rec center? Not that we're going to any gyms right now. But if we were, how would you test this? Using chi-square tests. Chi-square tests allow us to investigate associations between categorical variables like sex, political affiliation, race, ethnicity, preferences, geographic area. The list just goes on and on. There are two main types of chi-square tests. We have the chi-square test of independence, which is what we're going to focus on today. And this is going to test whether two variables are independent. For example, is happiness independent of your income? What do you think? And there's also a chi-squared goodness of fit test. It's used to test a hypothesis for just one variable, such as, is police brutality equal among different races and ethnicities? A little deep on that one. What do you think? Contingency tables. Again, we have already looked at some contingency tables. You remember there's different types of probabilities. We're going to use all that to do some chi-squared tests. So remember, a contingency table shows the frequency counts and probabilities for two categorical variables with multiple levels each. Below is the contingency table showing the counts for happiness and income level. Do you think these two variables are going to be independent? So here we have unhappy, neutral, and happy. Then we have lower class, middle class, and upper class and their corresponding values. So to do the first two, fairly easy. We wanted to know what proportion of people are unhappy. So we get the total number of people who are unhappy, 216, and we divide by the overall total, 1,733. And we end up with about 0.125 of people, so about 12.5% of people are unhappy in this sample. What about where proportion are middle class? We have 854, and we're going to divide that again by the total, 1,733, and we end up with almost 50% of people are middle class. So here are all of the marginal distributions for each level for both categories. So probability of being lower class, 31%, middle class, almost 50%, and upper class, about 20%. Here is the marginal distribution for levels of happiness. So it looks like 12.5% of people are unhappy, 57% of people are neutral, and 30% of people are happy. Which category do you fit into? I hope this one. So let's look at joint probability again briefly. Joint probability is the probability of two things happening. So in this example, let's say unhappy and middle class. So we have unhappy, middle class. So we're looking for this one. We have 83 people out of the entire total, 1,733, and we end up with 0.048. So about a 5% chance of being unhappy and middle class. Now let's move on to conditional probabilities again. Remember, conditional probabilities are the probabilities of a specific outcome for a categorical variable given a certain level of another variable. Remember, given means that you are already part of that group. So what is the probability of being happy given that you are in the lower class? Or what is the probability of being upper class given that you are unhappy? What do you think will have a higher probability? Happy given lower class or upper class given unhappy? So here is one quick example. The probability of being happy given that you are in the lower class is about 0.22. Those numbers come from, we have happy and lower class, and we are saying given that you are lower class. So this is the group we're going to use as our denominator. We can also say probability of upper class given that you are unhappy. So probability of upper class given that you are unhappy, we have 29. Given that you're unhappy over 216, we end up with 0.134. So you can calculate the conditional probabilities for all of these, but you have to condition on one or the other. So in this case, we are conditioning on income. What is the probability of certain levels of happiness given that you're in a certain income? And we can see from this that given that you are upper class, meaning that you are wealthy, there is a 40% chance-ish that you will be happy, 52% chance that you'll be neutral, and a less than 10% chance that you will be unhappy. We could also do exactly this, the distribution of income given happiness. So instead of using the row sums for the social class that you're in, we can instead use the level of happiness as the divisor. You would then just use the totals going downward on the columns rather than what we're doing here, which is row-wise. Now that we have our probabilities down again, let us move on to chi-squared test of independence. Now, based on some of the probabilities we've already seen, do you think happiness will be independent of the level of income that you make? Meaning, do you think how much money you make matters in how happy that you are? Or do you think that being a certain income bracket is related to your level of happiness? Let's test this hypothesis about happiness and income and see if they're independent. Just like before, we're going to use hypothesis testing. So the first thing we got to do is state our hypotheses. What do you think the hypotheses will be for a chi-squared test of independence, trying to see if two things are independent of each other? As usual, the null hypothesis is going to assume that there is nothing special going on. In this case, we are going to assume independence. Why? Think about that for a sec. We'll address it in just a moment. But here are our null and alternative hypotheses. Happiness and income are independent. Happiness and income are not independent. So why do we assume that everything is independent for our null? Because we can actually calculate what we would expect to see if the two variables were indeed independent. So if unhappiness and being lower class, the probability of that, if they were independent, should just be equal to the probability of being unhappy and the probability of being lower class, and you just multiply those two. This means that they are independent. The probability of both occurring, that joint probability basically, should just be equal to the products of their individual probabilities. So basically, we would expect to see joint probabilities if they were independent. So the research questions here are, is happiness independent of class, or do the two relate somehow? How do we go and get those expected frequencies? Well, we're going to take the raw tally of those that are unhappy, 216, and we are going to take the raw tally of those that are lower class, 537. We are going to multiply those two and divide by the overall total, and we end up with 66.93. That is what we would expect. If happiness and income were independent, we would expect to see 66, 67 right here. We see 104. So do you think these things are going to be independent? Now we can go and find all the expected frequencies for each possible combination of happiness and income level, and here they are. So again, we were expecting for unhappy and lower class, we were expecting about 67, we see 104. Or how about happy and upper class? We were expecting 104, we saw 135. So it's a little bit of variation there, but is it enough? Do you think that happiness and income are going to be independent? Step 2s and 3s. How about them degrees of freedom and level of significance? Well, we are going to test at the 0.05 as usual, but let's also briefly look at this chi-squared distribution. The chi-squared statistic follows a chi-squared distribution. Just like f-statistics in ANOVA, chi-squared tests are one-tailed because just like in ANOVA, they are always going to be positive. To get the given degrees of freedom, we will subtract 1 from each of the two categorical variables levels that we are testing. So we have happiness had 3 levels, we subtract 1, we end up with 2. We have income had 3 levels, we subtract 1, we end up with 2. Now once we have those numbers, we then multiply them together to get 4, and that is our degrees of freedom. So we're testing at 0.05 with 4 degrees of freedom, chi-squared distribution here. We can go and look it up on a table, and you will find that for an alpha level of 0.05, degrees of freedom equals 4. The critical value is 9.488. So just like with our other hypothesis test, we know that even if the null were true, that they are independent from each other, we won't get exactly the same values from our sample. But how close is close enough to assume independence? Is what we see close enough to what we would expect if things were independent? or is what we are seeing further out from the realm of reasonable null world that we can reject the null? And here is what the actual chi-squared test looks like. This is our step 3, choosing your test, and this is our chi-squared. We have the observed value minus the expected value. We are going to square it and divide by what we expected, and we are going to do that for all of the different combinations of happiness and income. So if you go and do all that lovely math, it looks pretty bad, I'm sorry. You end up with 54.04. And what was our critical value? It was definitely less than that. So what is going to be our conclusion? So let's draw our conclusions. We have our curve here, our chi-squared distribution. We have our critical chi-squared value of 9.49. We have our chi-squared statistic, 54.04, looking good. That means that we get to reject the null hypothesis. The observed frequencies are different enough from the expected frequencies that we can conclude happiness and income class are not independent. Let's try another one. Here we have the Titanic, and here's some Titanic data about the survivors. Do you think that being first class, rich, do you think those passengers were more likely to survive compared to third class passengers? Test if class and survival are independent at the 0.05 level. So steps 1, 2, 3, 4. Independent, not independent. 0.05, chi-squared, test of independence. We had 3 degrees of freedom, so we have a critical value of 7.81. If you go and get all of the expected counts, this is what they look like. And if you put them all into our huge chi-squared test, we end up with 190.4. That seems pretty significant to me. So our chi-squared test was 190.4 with a critical value of 7.81. We can totally reject the null hypothesis. Our data shows significant evidence to reject the null hypothesis that passenger, class, and survival status are independent. Instead, we conclude that on the Titanic, there is sufficient evidence to suggest that passengers, class, and survival status were dependent. Basically, the richer you were, the more likely you were to survive. Last one. Do you think that test grades and whether or not you studied are independent? Certainly not. Your test is very much dependent on how much you spend working on the class outside of class, like studying. So our critical chi-squared value was 7.84, and our statistic was 25.37. So we certainly can reject the null hypothesis that your grades and the time that you put into studying are not independent. All right, our last topic for the class. We will be looking at a different chi-squared test, but this time we will be assessing how well something fits what we would expect for just one variable. And for this, we need the chi-squared goodness of fit test. I will see you there. Chi-squared test of independence in R. As you saw with that really long, tedious process of calculating a chi-squared test, it takes a long time to do it by hand. So let's do it in R. Here are the 3 different examples that we did in this lesson. We have the first one of happiness and income. Here I am putting in the data. This looks a little bit messy because you have to put the data in a certain way, but here's the code to do that. We also have the Titanic data and your study habits and your grade. Then once we have the data in the correct form, all we have to do is say chi-squared test on this data set. That's it. And we get this. And here are all of the results that go along with what we did calculating by hand. We have our happiness, our chi-squared was 54 point something or another, and our p-value was really small. For the Titanic, also p-value super tiny, meaning they're not independent. And lastly, for study grades, p-value is also super tiny, meaning that they are not independent. Chi-squared tests are much easier in R, and I hope you give it a try.